Well, guys, good evening, everyone. So this is going to be, hopefully you can bear with us for another hour. It's going to be a talk about Swarm, the base layer service for the Ethereum ecosystem. It's basically a document document storage and content distribution framework. The idea is to have a serverless hosting system. And in the next hour, I'm very happy to have two other members of the Swarm team with me. Aaron Fisher is going to talk about the basic workings of Swarm and the incentive system that we are kind of currently researching and trying to implement. And hopefully, if I can, I take over and talk a bit about the storage incentives. And finally, Daniel is going to take over and talk about a bit of the Web3 experience that we hope we can have and offer with Swarm. So first,
hello everyone. It's good to be here in Berlin. So we're talking about Swarm, which, as Victor said, is sort of the storage file distribution layer. And I don't want to go into how it works too much because this was the topic of the talk at DevCon, for example. But just very quickly, overview so we're all on the same page how it works. Two things you need to be able to do: get data in, get data out. So to get data into the Swarm, how does this work? Well, the data is chopped up into tiny chunks, and each chunk is passed on from one peer to the next, and the chunk makes its own way to its final destination. Where it is to be stored is determined by the hash of the chunk, so each chunk has its own place. So as you can see here, I've marked the chunk address. That's sort of the same address space as node addresses, so we are going to try to look for the chunk at nodes close to this address. So this feeding in process called syncing, we push chunks closer to their address. And then when you get data out, it sort of works in reverse. You as the retriever, you make a request from some node that you're connected to, which is closer to the chunk address. That node will forward the request, will forward it, and at some point the request will end up at the chunk's location at the closest node, and the chunk will make its way back. So that, so very basically, chunks moving around is the base layer. What I want to talk about today is the incentives, because we are in Ethereum, we have the unique opportunity to also add incentives to make sure each node behaves according to rules that are beneficial to everyone. So, so incentivization is one. So let me introduce the problems that we're trying to solve by giving a very little history, so very brief history. So let's start with Web 1.0. So that means way back in the 90s. If you wanted a website, you had to do two things. You had to start your own web server or rent a server and publish your content, upload your content to save it there. Now, two things could happen. If, like my website back at the time, nobody cared about it, it just sits there. You have running costs for maintaining the server, but that's fine. If you were very lucky and your content becomes very popular and a lot of people care about the content you've produced, well, then two things happen. Your bandwidth costs skyrocket and your server crashes and goes offline. That was the reward, and nobody can see your content at all, but it's your content that they cannot see. So at least it had that going for it. Which leads us to the current situation of Web 2.0. Well, we can say we've solved a lot of the problems. We've got the cloud, which is cheap or even free. A lot of services offer you free hosting. If a lot of people want your content, they will spin up multiple nodes, it scales, and all is magic and wonderful and cloudy. And to get to this, we have entered what Donnie nicely calls a Faustian bargain, because we're paying for it in terms of privacy, in terms of censorship and centralization. So your content is no longer owned by you, it's often owned by the platforms you're publishing on. They will spy on all your users, they will mine all the data, and they make big profits, and you make a tiny slice of it, perhaps. And of course, these platforms can decide what gets published and what does not. So that's not really a good system, we think. We can do better. So the next question is, how can we do better? Could we use peer-to-peer networks? Right? So We all know some peer-to-peer networks. I guess BitTorrent is the most commonly known. Why could we not use BitTorrent to do our web apps, to host our web apps? It has many features we want. The content is distributed among many peers, and it scales nicely. The more people download something, the more it gets distributed, the faster you can get it. So that's a nice scaling built in. There's integrity checking built in. There's no central point of failure. But it's not good enough for web apps. It's good maybe to distribute large files, but for one thing, when you start a torrent, it takes a long time for the files to start. When you make the connections, get the first few bits. So it's not going to be very responsive. And there's no guarantee that your data will still be there if you're not actively running a node seeding the content, because you can't trust other people to do it for you, and they have no incentive to do so, because once you have, in the BitTorrent network, once you have the file, you disconnect and say goodbye, you don't care. So that's the situation we're in. So with that in mind, I want to introduce the Swarm incentive system and the two pillars that we've built it on: incentives for bandwidth usage and incentives for storage. So you will see why we have these two when we flesh them out. But the basic idea is, one is making sure the data is there when you want it. The other one is supplying the data when you need it. They're kind of separate. So the bandwidth accounting system accounts for all the bandwidth used and compensates nodes for providing data. The storage incentive system is to allow long-term storage usage and to compensate nodes for providing that service of storing content for a long time. So let me start with the bandwidth incentivization. There is no real way to account for total bandwidth usage. It's a peer-to-peer network. The best we can do is, for every peer, we're connected between peers. We can look at how many chunks we supply, how many chunks we get back from that peer. On a per peer level, those are two things: number of chunks supplied, the number of chunks received, requested, I should rather say. So the difference between those is our only real metric of how imbalanced our link is. So this is all handled by Swarm, which is the Swarm accounting protocol. This is the protocol that keeps track of all the chunks that you've provided, that you've requested. If I'm supplying a lot of chunks to you and you're supplying a lot of chunks to me, we don't really need payment. That can balance each other out depending on what kind of pricing we've agreed on. If at some point the connection gets very imbalanced, I get much more chunks from you than you're asking for me, I will have to make a payment. And we have a payment system that is off-chain by checks. So I can write you checks and you don't have to cash them in on the blockchain, because I should preface that it's impossible to pay for every chunk as it happens. There's far too many chunks flying around, it's far too quick, and making every payment on the blockchain would be very expensive and far too slow. So we need some kind of way to allow someone to get into debt, as it were. I'll give you a few chunks, and after a while I'm like, hey, I'd like some payment now, we've gone so imbalanced, and then you'd write me a check, and I can see that your checkbook has some balance, and if I don't trust you, I can immediately cash that check to make sure that transaction happens. But after a while, I might trust you, and I'll just wait until the checks accumulate, and only cash it in maybe once a day. I mean, this system allows for that, so it really allows for minimized transactions. All in all, what this adds up to, in the big picture, if I download a lot, I'll have to pay. If I provide a lot, I'll earn. I mean, that's sort of the big level. And then there's one other feature, which is really nice, which is sort of emerging from this system, is that the Swarm is auto-scaling. Because if every node always tries to make the maximum profit, then popular content will automatically become widely spread, and therefore will be accessible with more bandwidth and lower latency. And we don't have to build that in, that's sort of an emergent property. So that's the bandwidth side of things. Now, let's talk about the storage side of things. What are we trying to solve? So there's the so-called upload and disappear problem. We'd like a save button, like a save to Dropbox, a deploy to Swarm. Once, get the data out there, go away, I don't care about it, I know it's going to be there. And I want this to be true even if nobody is going to be accessing the data. So an example would be my website from 95, which probably nobody's going to care about. Or maybe I want to back up my own personal photos in an encrypted file format. Nobody's going to want them except me. So the nodes are not going to earn money by providing it, because nobody's going to ask for it. So in this context, we need a different kind of incentive structure so that I can guarantee that my files will be stored in the swarm. Well, so how are we going to do that? Well, we have to pay certain nodes to keep the data. I mean, that is the question is not what we have to do that. The question is how. And so a node can sell you a promise to store your data long term, and the way we've implemented it is that in order to sell such promises, you need to have a deposit locked in the blockchain, and if you lose the data, you lose the deposit, so you have a very strong incentive to keep your promises. There's a lot of subtlety here, because when do I pay you for storage? Do I pay you up front, and then you just disappear with my data and don't store it? Then I've lost my money. If I say, I'll pay you in a year, and then a year later, you say, I don't have the data, just forget about it. That's not going to help me either. So we need something which is agreed upon at the beginning, but can have an action at the end. So that leads us to swear and swindle, the two contracts that manage. So swear is the contract that registers the deposits. You register with a swear contract, you promise to store people's files, and here's my deposit. If I am registered with a swear contract, I can now sell receipts for all the chunks that someone wants to store with me, and these receipts that act as promises. And if later the data is missing, that receipt will be, hey, he's supposed to have it, I have the receipt to prove it, and that's the swindle system that Victor will get to in a little while. And finally, upload and disappear does work by the system of guardians. The system of guardians, I'm going to explain in the picture. So, the storing system works very similar to the original sync system, except that as the data flows into the swarm, there's receipts flowing backwards from the registered nodes. Each one that accepts the chunk gives a receipt that it's accepted it. And the owner of the file, which is you, want to say that you get to send the store request to the next peer over, which is going to be the guardian. And once that guardian has given you the receipts, you're out. You don't have to worry about the data propagating. You don't have to get a receipt at the final, from the final node, because all this chaining together can be handled at the time of litigation later. So, what happens then if data is not found? Like, it could be that somebody actually lost the file, or the chunk, even though they promised to have it. Or it could be something more mundane. The chunk isn't actually lost. I just couldn't find it for some other reason. Like, the chunk never made it to the closest node, or maybe the network grew and the chunk hasn't had time to be moved forward, and for whatever reason, I can't find it. I think somebody is reneging on that promise. I want to litigate. I'm mad. I have this receipt. I accuse. Me? I can do it? Alright. So, alright, we get to the swindle system, which is our litigation engine. Swindle is what's used to settle these disputes. So the first thing is, okay, is this loose somewhere? On some end. No. Hey, I have no idea where the loose. This is not nice. So what are we assuming? Or I don't know which part of this chain of cables is the broken one. Okay, so the first thing is, if we have a method, we're assuming that you can deploy your data and give public record of the guardian for certain data, so that if I see it, if I try to request a chunk and it's not there, I can accuse the guardian. So I will issue a challenge to the guardian to show me the data, or at least the guardian can, if they don't have the data themselves, which is most likely because they forwarded it on, they start accusing the next node, and that next node starts accusing the next node. until the chain ends up with, well, the two things can happen. Either the chain of accusations ends up with a node which actually has the chunk, in which case the chunk is returned and we're happy. And the other option is that the chunk should have been there, but it was lost. So in the example I gave, in this case, the string of challenges will end up with the custodian who has the chunk, and the chunk is found, it is returned, and the missing link is identified, the swarm can be repaired. So that's fine. So these challenges can help identify, find files that somehow been misplaced. But I mean, that's the good outcome. You find the chunk. If the chunk is lost, then the offending node is punished. Or rather, that is the stage at which you start invoking the blockchain. Up until now, this could all happen off-chain, but if you issue these challenges as the retriever and you do not get the chunk ever, then you will issue the challenge to the blockchain. Somebody can still present the chunk to the blockchain as a last resort, but generally what will happen is that the responsible node would lose their deposit. So that's their strongest incentive from actually losing it. So that's Swindle. Now, dealing with data loss. What happens if chunks do get lost? And we have to assume they will. In an ordinary insurance system, if a chunk is lost, I will get a big payout, some insurance compensation. This does not happen here. You cannot pay compensation for lost chunks because that provides an easy exit. I pretend to, you pay out your friends. So chunks could get lost. You have to be prepared. The best thing is to prepare in advance with erasure codes. So what this means is, when you take your file and you chop it into chunks, you get a whole bunch of extra chunks, which are called parity chunks, in such a way that even if a few of them go missing, you can recreate the entire data set. So the benefits of this, the owner of the data can set their own redundancy parameters. They can say how much extra data I want. If I inflate my file to be much, much bigger, I'll have maybe more security that the file will still be there, but I also have higher costs because there's more chunks I'm storing. And the other nice side effect is that the swarm can be repaired, because if you have data with parity chunks and then you notice some chunks missing, well, you can recreate the chunks as soon as you notice them missing and feed them back into the swarm. So a single chunk loss is not detrimental, but if you don't have parity chunks and one encrypted file, a single missing chunk renders your entire collection moot. So it's important to prepare. Not going to talk too long about the implementation, but down here is our file broken up into chunks. The way the swarm works is we hash the chunks. All these hashes are bundled together into chunks of their own, and so on, all the way up. It's nice little Merkle tree. And we add erasure code at every level. So this would be a typical component of the erasure coded tree. So at every level, you've got extra redundancy bytes. And you don't care where your chunks get lost. Any chunk in the tree is equally important. They all have the same kind of extra parity data. And any node trying to access this kind of file can notice if there's a chunk missing and can repair it, which is nice. And there's actually an incentive to request all the chunks, which is also a nice side effect. A priori, I only need to request the data chunks. I don't have to care about the parity chunks at all, unless I find one of my data chunks missing. But if I just request all of them, all I can do is just take the first, whatever comes first, I'll accept. So I'll manage to recreate the file quicker. I have a lower latency at the cost of higher bandwidth. Like, I need to download more stuff, but that'll be quicker. So it could make things more responsive. So that's the erasure coding, that's the preparation. But that's not enough. The other crucial point is that we need to be able to monitor large data sets and see when chunks go missing. So this repair is not going to happen automatically. And for this, Swarm does include an audit system. So instead of having to download the entire file to see that everything is still there, you can launch an audit which gets passed on from node to node. It looks somewhat like this, where you launch an audit, it gets transported node through the entire swarm and comes back with an answer, yes, the file is still there. But the details of this, we're not going to cover today. That is part of our... Unless you want it, we'll talk you through this diagram, no problem. But it's part of our Orange Papers publishing. Orange Papers, you will find this system explained. And one more point about this audit system, it can be used as a condition for payments. So for conditional escrow. Going back to should I pay at the beginning or should I pay at the end, what we can do is put up a payment up front, and at regular intervals, we perform an audit, and the result of that audit, which is a proof that the file is still available on the swarm, could unlock the next installment of the payment. So we can have a continuous payment, and each little new bit of payment is only released when the proof is supplied that yes, the file is really still there. So that's swap, swear, and swindle, the incentive layer. And with that, I will hand over to Don.
Hi everyone. So what I would like to talk about is the upper layers in this graph. So all what has been so far explained happens on the very lowest layer in how chunks are being passed around, and above that there are several other layers, and of the greatest interest to developer is, of course, how do you create swarm hosted distributed applications. So that's what I'm going to cover today. So first, what we would like to achieve. We would like to achieve a user experience which is familiar to web users. So it should look like a website. It should look like a web application. And also we have similar quality criteria. So it should be interactive, responsive, intuitive. It should feel like web. So it's Web 3, but it's still web. However, because we are having distributed applications on a blockchain controlled system, some things will necessarily be different. One of them is identity management and personalization. So this will not be part of applications. Application developers will not need to worry about these things each time they write a new application. It will be kind of part of the infrastructure. And as you have, those of you who have seen the preview releases of the Mist browser, you have already seen that you can browse with different personalities. So you can be, your personal account or your role in your company. So you have multiple personas, and you can select one of them for whatever you're doing with the application at the moment. And this functionality, it will be built into it is actually already built into the browser. And another very important difference in the experience is that instead of, doing these ritual click-through contracts that do nothing, actually your interaction with the web application will involve financial and legal consequences. So you can enter into actually binding agreements that are going to be enforced by the blockchain. You're going to make payments, and you will going to receive receipts that actually prove something in case you need it for later litigation. And you also can have things like rate limiting your payments, or certain kind of payments or certain kinds of transactional activities will need a password-based confirmation. So if you click something, then a window popping up asking whether you're sure may be not enough. For example, if you're submitting your will or something like that. So then you need at least a password, but maybe somebody else's signature as well, as a notary. So all these things will feel a little different from how they feel currently with web browsers, but this is just additional functionality. So that's how the user will see it. So how the developer is going to see it. How a distributed application is built, how it functions. First of all, once you develop it and upload to Swarm, and as a developer you're happy with how it works, then what you need to do is you take the root hash of the entire file system that comprises the files of your application, of all the static and dynamic data, all the static data, sorry, not the dynamic ones, and you register it on the blockchain, which binds it for everybody else to some user memorable name. So it feels somewhat similar to uploading it to a server and then registering the domain name for it. But first of all, it will involve a lot less hassle. And secondly, all of it is going to happen online on the blockchain. So there will be no paperwork and so on. And it can happen very quickly. So basically, until your transaction receives enough confirmations on the blockchain, you're done. Most of the static and dynamic content of your application will be in Swarm. So for static content, it's obvious, you have just uploaded it. But also, as users interact with your application, they can upload stuff into Swarm and place the hashes where they belong. And this goes, and where they belong depends on who is interested in those changes. So global state changes, if you publish something as a user, or you make some change that affects all the other users, then there's no way around it. You have to publish it on the blockchain. But the other end of the spectrum is that some changes only affect you, like for example your settings. They can be stored locally. You don't even need to upload them anywhere, but of course for convenience, so that you can access it from multiple devices, they can be backed up either in Swarm or on the blockchain, even if it's that important, but still you're only concerned about them locally. And another very interesting feature that as a developer you always have to keep in mind is that most of the business logic gets executed by the individual computers of the users. And as you cannot trust them to follow rules, you need to kind of tie it in so that whatever they do, whenever there's a point of contention or something that you need assured, you need to tie it in to be verified through the means that are provided by Ethereum. So, but still the execution happens locally, and that's very important. So you need to make sure that the burden is sort of distributed evenly, which is kind of a challenge. For example, if you want to have a search service, then you need to provide an index which is very rapidly searchable on the local machines of each user, because you cannot outsource it to large clusters, because all you have is a distributed peer-to-peer system. So I would like to show you a few examples of how things are being done. The first example is actually already implemented. It's part of the Swarm examples, and it's about the simplest distributed application that makes some sense. So it's a distributed photo album. You can edit it, you can add photos, you can shuffle them around, so it's somewhat similar to Picasa or something like that. And when you want to publish your photo album so that others can see it, you simply publish the root hash of its current state on the blockchain. The long-term incentives that Aaron has explained will make sure that it's not going to be garbage collected out of Swarm, so it will stay there. And the performance is also taken care of by Swarm, so you don't have to pay extra cost if suddenly you will have a bunch of people interested in your photo album because you have just accomplished something remarkable and everybody wants to see it. The reason this is so easy because there's no concurrent editing. So all the editing happens by the same person or the same entity, let's say that. And because of that, you don't need to reconcile conflicting edits. And also there are no comments or ratings in this example. So this is a one-to-many broadcast, and that's basically how it works. You can look at the code. It's fairly straightforward. The second example, it is not implemented yet, it is basically an add-on on the first example. So let's say you want to have some kind of a social network. You can think of Facebook, but not necessarily. So you can think of a blog engine, you can think of just adding the rating and commenting system to your movies or your photos. So anything that involves interaction between different users and content that can be changed. So in this case, personalization boils down basically to a finite list of followers. And because of this, so it's either friends who are commenting and liking, or it may be some authorized editors or something, but the point is that each piece of content is edited or at least contributed to by a reasonable set of contributors, which is not infinite. And when you're, let's ask questions later. So the rendering part in this case needs to be structured in such a way that it traverses this whole list and builds together the DOM of the rendered content in such a way that it collects all these contributions and reconciles them. And for each participant in this case, you need a root hash. And each time they do something, so each time a person does some editing, of course they can be aggregated, but anyway, after you're done editing, you need to publish something on the blockchain. With side chains, you can make it more scalable, but I think that for a long time, one little transaction per contribution is an acceptable cost. And also things that change the structure of this social network, initially like friend requests, they will also best be posted and communicated through the blockchain, but of course various blockchain scaling techniques can apply here as well later on. For now we have, so these two examples are basically follow one the other, but we are mimicking stuff that has been done on Web 2. So this is basically how you transition from Web 2 to Web 3. However, the third example is something that I think cannot really be accomplished in a Web 2 context. So when you have large knowledge bases, like encyclopedias and maps are two prominent examples. So we do have Wikipedia and we do have OpenStreetMap, but both of these projects are grappling with the problem that they somehow have to come up with an official truth. Like, what is truth? And the reason for that is because in a Web 2 context, forking and rebasing and merging and all these things, which we know from GitHub, they are expensive. So what these kind of technologies that we're currently working on will allow is to present the entirety of human knowledge on a given subject from different perspectives, because alternative perspectives do not face prohibitive costs. So it is generally true that on any given subject, opinions tend to cluster around a few opinions. And on the rest of the world, people tend to agree. So precisely because the way Swarm is structured, that if you want to clone a database and change some little parts in it, it's cheap, because everything that is the same is hosted and referenced from the same hash, and it's the same physical chunks stored by the same machines. You don't have to move around large amounts of data. So from that point on, you don't have edit wars. Simply, if there are different perspectives on a given topic, it can be some event in recent history, or it can be something like which country a certain piece of disputed land belongs to, what country is Liberland. So these things can be resolved very naturally. And the other thing is, because of the distributed nature, you don't get blackouts. So when Wikipedia Foundation is protesting something and they black out Wikipedia for the day, that sort of creeps me out, because like Wikipedia is a resource that many people rely upon, and if there are a few people who can decide to black it out, it's really bad. I mean, it's good that they're nice people and that they don't abuse their power, but it's better not to have that power. So with these kinds of databases, you can either compare the different perspectives that exist on a given topic, and hopefully there aren't too many, because that's usually the case. And also you can sort of, publish your version. Like, this is how I think. Like, this is the world according to me. This is my personal edition of the world map. And so these are the kinds of things that become really cheap with a swarm-hosted knowledge base. And I would really like to see these kinds of applications emerge, and hopefully some of you get inspired and do something like that. And that concludes our talk.
Just before we finish and give it over to you for questions, I would like to mention a few points on our roadmap. So first of all, we're working on. We mentioned that we're in a unique position that this content distribution system is directly interacting with the blockchain. So it allows for certain synergies in a much easier way. So for example, it can allow you to link certain browser events, like basically user behavior while surfing, to particular blockchain events. So and we would like to put a little bit more work on this and try to come up with some sort of standards how to represent, for example, triggering transactions by visiting a link, or some sort of requirement, for example, to have provable licensing on an intellectual property. It's obviously, I'm talking about the ideal world of post copyright statement, like you basically have consensual networks where you opt in to respect royalty to content producers, as opposed to that necessarily like state prosecuted enforcement of these rights. So for this kind of basic protocols on the level of browser and blockchain interaction, you can implement very, very interesting features that are relevant to maybe artistic or intellectual property publication and distribution systems. Notably, attribution. So, for example, just using a similar system to the Ethereum name service that Nick Johnson is currently implementing. You can use that for a system similar to a Scribe, for example, to register original content. You can have systems which require, for example, certain content to have a provenance chain leading back to some sort of original work, so that will represent, say, derivative works, and you could verifiably have access to licensing information about all these derivative works, etc. These are just examples which are at the moment pretty handy, admittedly, and a bit of science fiction now, but we can see how these things can be done. Just simply the fact that swarm usage can be linked directly to blockchain manipulation, so transactions. Okay, so a little bit about other ideas on our roadmap. So obviously, Aaron mentioned that in order to implement the storage incentive payment system, we need to have some sort of really efficient micropayment system, and for that we're planning to implement a payment channel network, which is very similar to Raiden. So hopefully we're gonna have synergies and work together with the Raiden team and join forces. And hopefully the database stuff that Danny was talking about, basically think about that feature as providing the M in the traditional LAMP stack idea of web applications. So where you have like Linux server, Apache server, MySQL, and PHP. Then the equivalence in the Web3 world would be like Swarm as the hosting layer, Mist as the server layer, rendering layer, and the database would be a distributed database over Swarm. We kind of toying with the idea to have the database implemented on a similar way to a level DB, and I'm kind of thinking of applying some sort of extra layer on it, which makes it possible to do querying and decentralized indexing of it. This is also a bit of the usual things. So other than that, we have plans to use this kind of structure to put the blockchain and the state data of the Ethereum blockchain on Swarm. That's a very interesting project because that allows basically to have a totally scalable solution for basically analog transition from full node to completely light node. Because by simply controlling how much of your disk capacity you use for storing the blockchain, you can basically set whether you are full node or archive node or light node. And obviously it also scales in terms of if you're a lighter node, then what you actually gonna end up storing is stuff that you retrieve that you were interested in. It's a bit similar. It has similarities to the Facebook example that we have here. We also have on the roadmap some refactoring on the Swarm code base. We definitely gonna refactor some of the modules to comply with the IPFS protocol standards, which will give us a very interesting opportunity to swap certain modules between the two systems and try out whether the IPFS existing implementation for, say, DHT and like the actual storage layers is more efficient than what we have before, and conversely, the modules that we develop and they might not can also be used by them. For example, the erasure service or the proof of custody units. Yes, sure.
Where can you example it?
The photo album example is in the code base. So you find the Swarm current code under the Ethereum Go Ethereum repo. It was not mentioned so far, but the implementation that we're working on, the reference Swarm implementation, is written in Go, and it's part of the Nest implementation. So the Swarm code is in the Go Ethereum repo under the Swarm branch. So not in the main develop branch. It's not yet. Yeah. So
I think that speaking of the roadmap, I think it's important to talk about the next step, the next immediate step that will be visible to the community. That one of the Geth versions that are going to be released soon. We don't know which one, but hopefully one of them will be Swarm capable. So we are really close to that, and it will include of the incentivization systems. It will include Swap. So Swap has already been implemented, it's being tested, and it seems to work. So
it also very likely that at the time that this code launch will happen, we're gonna have a Mist release as well, like basically Mist Okay, Swarm getting released. So sorry, just to finish up like this synergy part. So let's open up the questions. Thank you.
So, I have several questions. I can ask them later. That was work. Looking forward to using Swarm. So, simpler question is, you run and with regards to synergy, so I think that's how to do that. And I guess also from what I gather, this Swarm doesn't have a stack, it has something else, or does it?
Yeah, it has something else, but it's basically the same.
So these things are so similar that so if you think about what these systems do at their core,